the whole engine and the ship will start vibrating. Rahul Kumar Patel will come back. Kshitij Jaiswal was removed from the meeting. Sorry, Kshitij, did not intend to remove you. I just my thing had felt on the wrong. Admit all and deny it. We are very close to each other. So we can try again. Rishi Pandey, Prashika, Manohar Singh, everybody is here except Jaiswal. I hope Farhan Akhtar is here also. Okay. I think Jaiswal, I pressed the wrong button. So what I was saying, while you're, yeah, he's come. Okay, he's come. Okay, sorry, Jaiswal, I pressed the wrong button. I deny entry. I'm not going to deny entry to anybody, even if you're a little late, okay. Because I had the same experience. My internet was not coming on and I could not be in time. So I suppose it's the same with some of the boys. And since you have nothing else to do at home, I know everybody is interested in coming for some sort of class. You have to be active with your direction towards your profession. So that is why I know everybody wants to come in and we are trying to explain. So I was just explaining to you critical speed. It is the speed at which very severe vibration takes place on the ship. And it's a very interesting situation. Why does it happen? It happens only at a certain bandwidth. Suppose your propeller RPM, that means the shaft RPM is from 0 to 110, let us say. 110 is the full speed. So between 46 and 52, between 46 and 52 revolutions per minute at that bandwidth, there will be very severe vibration. This happens on the ahead direction as well as on the astern direction. Is not much of a difference for an resonance velocity. Resonant velocity is being a little verbose. It is being verbose, resonant. Of course, resonance takes place and speed takes place. I don't think there's much of a difference. It is the speed at which very severe vibration takes place. And I suppose it means the same thing, resonant velocity. Now, velocity is, straight line movement possibly, but RPM is rotational, angular velocity. If you say resonant angular velocity, then it makes sense. But if you simply say resonant velocity, I don't think it will make much of a difference. Angular velocity will be the correct term. But in simple terms, it is critical speed. Okay, now why does it happen? First, let me tell you where it happens. It happens between a RPM of, say, suppose 46 RPM to 52 RPM. And this happens in the ahead direction as well as in the astern direction, and absolutely symmetrical. That means 46 RPM to 52 in the astern direction, 46 to 52 in the ahead direction. Now, I have just given you figures 46 to 52. It might be 44 to 50. It might be 50 to 56. But around that region, between 40 and 55, I will give you that is within that bandwidth, about 5 to 6 RPM is the period where you have a condition of very severe vibration. Now, why does it happen? Okay. Now you see the entire shaft system, that means the crankshaft, the intermediate shaft, tail end shaft, and the propeller, they are all bolted together. So the whole unit can be considered as one shaft. Now this shaft has a natural torsional vibrating frequency. A natural torsional vibrating frequency. What does it mean? What it means is, if you need to understand natural frequency of a torsional nature, the radial nature is understood. If I hit it, it vibrates. But what kind of vibration is that? It is sort of side to side, transverse, anyway in the direction. But torsional frequency is, suppose this end of the shaft is fixed and this end is free, and I attach a rod with two masses at the two ends. I twist it and I let go. What will happen? The whole rod will vibrate and then it will come to a stop. It will vibrate, but at a particular frequency. And that frequency is the natural frequency of the shaft. If the shaft was longer, then the frequency would be different. If the shaft was shorter, it would be different. If the shaft was thicker, the frequency would be different. If the shaft was thinner, again the frequency would be different. So everything depends on the moment of inertia of that shaft. It is mass that is responsible, length that is responsible, and the internal resistances of that material. So that is the natural frequency of the shaft. Okay. So everybody now understands what is natural torsional vibrating frequency. Okay. Now consider the engine starting from 0 RPM to 110 RPM. Okay. So as it comes to, I told you 46 to 52. Okay. As it comes very smoothly up to 45, everything is fine. You are very comfortable. Moment it touches 46, 47, and then you suddenly see the engine and the whole ship starts vibrating. What happens during this time? You see, when the RPM is from 0, the frequency is proportional of the frequency of the peak torques. In other words, the peak pressures which occur in the cylinders. If there are 6 cylinders, let us say the firing order is 1, 5, 2, 3, 4. Okay. So number 1 gets the force on the crankpin first, then number 5 gets the force, and then number 3 gets the force, then number 2 gets the force, then number 4 gets the force. So in order of the firing order, the peak pressures act on the crankpins. The torque is not a very uniform torque. It is one moment in this unit, one moment in that unit, next in another unit. So these are firing forces which are ultimately causing a force on the crankshaft. Okay. If the frequency of these forces acting on the crankshaft becomes equal to the natural torsional vibrating frequency, then the whole shaft begins to vibrate so severely that the entire bed plate, engine, ship, hull, everything vibrates. So it is the speed at which the frequency of the peak pressures, frequency of the peak torques coincide with the natural frequency of the shafting system to result in resonance. Now, that is shown in this diagram. Here, you see in red that red is the natural frequency of the shafting system, and then the same frequency of a little larger value is the frequency of the peak pressures or the firing torques. Okay, so moment these two are coinciding, you will see both of them have got the same wavelength. Initially, they don't have the same wavelength. The natural frequency has a fixed wavelength, but as the RPM starts slowly for the engine, the wavelengths are much larger. But as the RPM keeps increasing from 0 to 45, the wavelengths keep getting shorter because the frequency starts increasing. And then the frequency increases to a value which is equal to the natural frequency. And then you have the amplified frequency, which is shown as a very large amplitude. So this is what happens during critical speed. Natural frequency and forcing frequency, they synchronize to cause severe vibrations. Okay, so that explains critical speed. The so-called critical speed is that at which the torsional forces created by the firing impulses and the reactions from the shafting system with the propeller synchronize with the natural frequency of the shafting to give amplified torsional vibrations. These vibrations reverberate through the entire ship. Such effects can result in severe damage to the marine engine's internal moving parts, cracks in the structure, loosening of bolts, securing arrangements, and damage to bearings. Vibrations of marine engines is mainly due to axial vibration and torsional vibration, or a combination of both. Okay, I think this is reasonably easy to understand. So let's have a look at how fatigue failure, this is plate 26, how fatigue failure takes place. Now, if this critical speed was made continuous, the shaft will definitely fail. The extent of vibration, that means 2 and 4 of twisting of the shaft, will cause the shaft failure. No matter how strong the shaft is, it is going to fail. There is a limit to which the material can sustain a stress, and that is called ultimate tensile stress. So it will fail. Now let's have a look at these pictures. You see at the bottom here, bottom right hand side, is an indication of how a fatigue failure will look like. This is a shaft which has gone through a fatigue failure. If you remember when you study strength of materials, when a shaft is twisted, the maximum stress arises on the surface. All right. Minimum stress arises at the core, at the center of the shaft. There it is a neutral axis, so there is almost no stress over there. The stress generally takes place on the surface. And if on the surface you have a dent, you have a scratch, you have a pit mark, that will become the origin of starting a crack, of starting a failure. That is why whenever we take out the bearing from a shaft, somebody puts a cloth over it and wraps it out with a cloth and ties it with a rope. Why? Because if by mistake somebody drops a spanner or strikes that surface will maybe have a microscopic dent in it or a scratch in it. And that scratch will become the origin of failure. So we need a smooth mirror finish on the crank pin, on the journal, on any part of the shaft. So that is why we need to have a mirror finish on the surface for a crank pin, for a main journal or any shaft. If there is a dent, if there is a scratch, it will fail. Now, in some crank pins, or rather all crank pins, I will say, there is an oil hole. All right. So that oil hole has to be made very carefully. It is not any random oil hole for the oil to come out. It is made at a section where there is minimum stress, or what do you call that? Neutral axis. Okay. Now, suppose this is the crank pin and it is being forced in this direction. So the opposite direction will have the maximum tensile stress because it is going to bend. Because the force from the connecting rod is going to make that connecting rod bend. If it bends, opposite side will have tensile stress, and the side where the force is acting will begin to have compressive stress. Now, if the oil hole was made in that point, it would tear apart from there. Where is the neutral axis? Exactly at right angles to the line of force of the connecting rod. So this side will be the oil hole. So that oil hole is made in the neutral axis to minimize the stress at that area, because that is the point which will not bend. It is at neutral axis. If you bend it, this side is compressive, this side is tensile. What about right angles to the surfaces? They are a neutral axis. So the oil hole can be made there. And that is how you minimize the stress at the region of the oil hole, in spite of claims being that the shaft has failed from the oil hole. Well, sometimes it can happen if the hole does not have a correct fillet radii. That means it has a sharp change of section. So that is why the holes at the entry are made smooth, so that there is minimizing of stress concentration. Now let's look at this shaft here on the down bottom. The origin of failure has been right at that tip, or rather on the circumference. And once it failed from there, the failure continues gradually, and these beach marks, they are called beach marks, because if you see on the beach, the sand marks, because of the tide that comes in, it makes marks similar to what you see on a fatigue failure representation. So these marks will continue as the cracks go deeper and deeper. Then there will be some stage where the strength of the rod is not enough to create resistance to the torque that is being applied. So the remaining part of the shaft will break suddenly, and that breakage part will give a surface which is very rough in nature and shiny in nature. Because when you look at it, you see spangles, the steel spangles which are fresh, exposed to atmosphere. And if you delay that in 2 3 days, it will become rusted and it will not look new anymore. But the fractured part, this will look old because this has opened up to the atmosphere. It has partly oxidized, so it looks old. That the breakage has been old. But the lower part, what you see, will look fresh. Of course, if you detect it immediately. If you detect it after 10 days, that side will also look old. But immediate detection will show that this part is shiny, nascent, metal exposed. Okay, so this is how it happens. Now, in this one is the real picture. It is a photograph of a shaft that has failed out of fatigue failure. You see, the failure has started from the surface of this region. The crack has opened and the material has failed here, and thereafter the crack has gone deeper and deeper and deeper into the shaft till such time those striations means the spaces between the lines. They are called striations, and the marks which border them are called beach marks. All right. So it has reached up to a certain level, and thereafter the rupture has taken suddenly. So this is also a shaft where the failure has emerged from the surface. Now, these are two shafts which are showing you where the failure has taken place from the surface. But you have a look at the shaft which is in the middle over here. There, it is not from the surface. There has been inherent flaw inside the material, and this has been and this region. So the failure has started from this point, and the crack has been expanding readily in all directions. So the separation of the surface has been expanding separately in all directions till the one closest to the circumference has reached the limit. But on the other side, the crack continued till such time there was not enough material to support the resistance, and then the entire shaft has fractured. So not all shafts fail from the surface. There may be an inherent flaw inside the shaft, something like if there is an impurity, if there is an internal fracture on account of stressing. You see, sometimes the shaft has got internal stresses, and that stress has caused the crystalline structure to separate. Even if one crystalline structure element separates, it will become a cascading effect, one after another, one after another. That is called a cascading effect, and the crack will keep expanding. So that's how fatigue failure starts. Now let's have a look at the crankshaft. You see this part of a crankshaft, it has failed. You see, this part of the crankshaft looks, there are no issues for it to fracture really. What has happened, it has broken from this end first. See, that hole over there is actually an oil hole. This oil hole has possibly been the origin or the cause of failure. Now, if this side fails, automatically the other side gets stressed out very severely. If it gets stressed out, it cannot take the load, and then it fails. It is something like two cadets holding up a load. Okay. Suppose if two boys are holding up a load from two ends of a stick, and in the middle there is a big load, and one boy takes off, that means he stops taking the load. What happens? At least conceptually, the other boy gets the entire load to carry, and he cannot take that entire load, so he breaks. So everybody thinks that fellow is the one who has failed. He couldn't take the load. It is the other fellow who was the dodging out and caused the other fellow to fail. Same thing, same principle goes in bottom end bearing bolts. You see, when one bolt becomes loose, what happens? If it becomes loose, then the other bolt gets the full load, and that other bolt cannot take the full load. It has to take 50% of the load. But is given 100% of the load, it breaks. So everybody thinks that bolt is the one that is to fault. It is not that bolt to the fault. It is the bolt which has become loose, but it has not broken. That is the one that is the cause of breakage. Similarly, here, this side breakage has taken place because this side has failed. If one side fails, the other side gets the full load, which it cannot take. So it is broken. And see, this particular one has broken from where the oil hole is. This is the weakest part of the material. It is not in continuity. So that is why it has failed. Now let's have a look at this crankshaft. See, this crankshaft here has broken from the crank web. The crank pin is intact. Over here also crank pin is intact. Here crank journal is also intact. The crank pin is intact, but the web is broken. But you see, where the web is broken is the point where the pin and the web are very close to each other. That is the usual point where they fail. That is called the fillet radii. I told you how much should be the fillet radii, 0.05 D. If you remember, when I was teaching you about the crankshaft, the diameter of the, or rather radius of the curve at the point where the crank pin meets the web has to have a curvature, and that curvature is called fillet radii, because the radius is in all parts, all around, on both sides. So the plural of radius is radii. So that curvature has to be of the correct dimension, because the crank pin has a sudden change in cross-sectional area as compared to the web. And where there is a change in the cross-sectional area, that is where the stress concentration takes place, and most failures arise from that point. More than the oil hole, the point at which the crank pin meets the crank web is the point of failure, usually, mostly. Secondary ones are, you see that oil hole over here. In some cases, the crank pin fails where the oil hole is, because probably this side is not seen, but other side of the crank pin will be the emergence of the oil. And that oil hole is because of reduced material to take the step, and failure arises. So these diagrams you can actually produce in case you're explaining what is fatigue failure. Here is that same diagram which is there, and this is the initiation. He has called that as the initiation, that means the start of fatigue failure. And it continues till such time there is not enough material, and then the entire item fails. Ravi Prakash, he's come pretty early for the next class. Okay, so propagation of fatigue crack evidenced by beach markings. You see, these lines are called beach markings. These lines are called beach markings, and that is actually fatigue crack propagation. It keeps increasing step by step, and each of those steps is given by a beach mark. Catastrophic rupture when the crack length exceeds a critical value at the applied stress. That means how far from the original crack to the last crack, because that place the material is not joined together, it is already separated. The remaining part of the shaft which is separated does not have adequate area to convey the torque, and it fails suddenly. Now, because of these vibrations, you have had failures. Now, to avoid failures, you will need to create damping. Damping is reducing the vibrations to as much as you can. In fact, on board the ship, you as an engineer, you will be on the alert everywhere, and you will require to dampen out the vibrations wherever you can. You suddenly find some clamp has become loose. Could be pipeline, it could be a foundation of a pump, it could be anything, any part of the machine which suddenly starts vibrating. You need to take initial care. You see, there are times when the clamps which are holding the pipes in place, they become loose because they are also vibrating. And if they vibrate and they become loose, the entire pipe starts vibrating inside. Sometimes you cannot hear it, sometimes you cannot see it. But one fine day you suddenly find ruptured, pipe has ruptured and oil is leaking out from there. A small leak. And you look and you find the pipe has been hitting the support on which it is clamped. and that place has been worn out, and it has worn out to the point where the crack has emerged, and from that crack oil has started shooting out. So what are you going to do? You will immediately require to put band-aid. What is band-aid? Band-aid is a jubilee clamp with some rubber gasket, put it round out with a band and tighten it. That is your temporary measure. You stop it. And also at the same time, you have to make some arrangement where the vibration has to be stopped. For a quick resolution, you marine engineers have to be very, very resourceful. Sometimes a situation arises where you need to take immediate action. So what will you do? Immediately you take a rope or a wire and put it around another pipe and tighten in between, rotate it in between. So the whole pipe is pulled against another pipe and that vibration has reduced. This is your immediate first aid. First aid measure against a ruptured pipe. First is put a jubilee clamp, tighten it, stop the leakage because that oil can catch fire. Then you get hold of wire and put it around another pipe and twist it so that the vibration stops. That is your immediate control. And thereafter, you next is clean up that oil that has leaked out. Otherwise, it's a fire hazard. Thereafter, when you get the chance and time, space, and the material, you arrange to repair that pipe. You may have to stop the oil from there, take out that pipe, do a little welding, then reheating to reduce the stresses that are developed, and then put it back in place with a cushion and tighten the clamp and make sure it does not vibrate again. Or you may need to crop that pipe if it is been worn out after repeated hitting and it cannot be welded. They need to crop that pipe, put an insert, weld the whole thing around, and then put it back in place. So these are measures you will need to take and be very, very resourceful. Marine engineers are supposed to be very resourceful. Any situation happens, they have the means to repair it with no help from outside, no help from shore because shore is not available. Okay, so this damping, as the name suggests, dampers are used to dampen or reduce the frequency of oscillation of the vibrating component of the machine by absorbing a part of the energy during vibration. After all, vibration is energy, energy being manifested in the form of movement. Okay, so this energy has to be absorbed. So this energy, once you absorb it from that vibrating body, it will stop vibrating. Okay, if you put a clamp and tighten it, that energy is being absorbed by the clamp and the base which is holding that clamp. Now, I told you that there is axial vibration of the crankshaft. The axial vibration is dampened out by means of an axial damper. The axial damper is fitted on the crankshaft of the engine to dampen the shaft generated axial vibration. That is the oscillation of the shaft in the forward and aft directions parallel to the horizontal line. Now, if you say along the axis, it obviously means it is parallel to the shaft horizontal line. So if the shaft is moving axially, you need to put a damper. Okay. Okay. This axial damper, it consists of a damping flange integrated to the crankshaft and placed near the last main bearing girder inside a cylindrical casing. The casing is filled with system oil, that is crankcase oil, on both sides of the flanges, supplied via a small orifice. This oil provides the damping effect. Actually, it requires a little more explanation. Okay, how do I dampen out this axial vibration? Now, a principle is very simple. We have an arrangement which is like a piston, and this piston is a moving piston, and this piston is fixed to the shaft which is vibrating. So the whole piston is moving. Now, if you have a liner with piston rings on it, then what is on above one side of the piston is going to be compressed or expanded, compressed or expanded. On the other side also, if you have put a stopping device, That means the piston in the middle will be compressing this side or it will be compressing the other side. Okay. Now put oil on both sides of the piston. So the piston will start compressing the oil this side when the shaft moves in this direction, and piston will start compressing the oil in the other direction when it moves in that direction. So the same principle is used for the shaft. On the shaft, you have a flange. Okay, it's not a very thick flange; it's a reasonably thick flange, and it is part of the shaft itself. Okay, at the rim of the shaft, you have a sealing ring. Okay, now this flange works like a piston. Outside this flange, you have a casing. This casing has got two spaces. One is on this side of the flange, one is on this side of the flange. Right? Now this casing has to be held somewhere because if the shaft is moving, the whole casing can't afford to move. So this casing is then fixed to the transverse girder of the last bearing. That means the forwardmost bearing. Okay. Forwardmost bearing, which is a free end. You cannot put it in the aft end because the shaft has to come out from the engine and then have the flywheel, then you have the intermediate shaft and the propeller shaft. So obviously it cannot be fitted on the aft end. So it has to be fitted in the free end of the engine. Okay. At the free end, this casing, which is including the flange of the crankshaft, the casing is fixed to the transverse girder of the last bearing. So any force on that bearing axially is transmitted to the transverse girder. And the transverse girder is part of the bed plate. So the whole bed plate takes the whole axial force for dampening out any axial vibration. So I have a diagram here which will help you to understand how it works. Now, just now I said on the crankshaft, or rather extended part of the crankshaft, you have a flange. And this flange has a seal ring at the rim of it. The seal ring can be any Teflon, it can be, it is like a piston ring, but it is fixed. It does not have compressibility. It is fixed. Most likely it is ebonite or it is polytetrafluoroethylene, or it may be some grade of bronze, soft grade of bronze or brass. I'm not sure exactly what material the steel is, but definitely it has to be a mean which is not a hard surface, otherwise it will damage the casing in which it moves. So in this casing, oil is fed in to both the sides, all right? And this oil is fed in through an orifice. This orifice, this valve is actually a throttle valve. This throttle valve acts like an orifice. Orifice is a small passage, but this throttle valve can be varied. That means the diameter of that passage can be increased or decreased. And this setting is done by the manufacturer himself. We don't go upsetting it. So when the piston or when the shaft moves in one direction, the oil on one side of the flange is compressed, and the oil, this compressed oil, needs to be released. It is released through the orifice at a regulated speed. So that helps in the shaft moving at a regulated speed. Similarly, when the shaft moves in the opposite direction, the oil on the other side is compressed and the oil goes again through the orifice speed. At all times, the oil pressure is maintained from the normal lubricating oil pipeline system. Okay, let's have a look at the diagram. If you have any questions, do not hesitate to ask. Now here on the left side of the diagram is the assembly for the axial vibration. Now this unit right in the middle is the casing for the axial vibration damper. And if you see at the bottom, it is attached to the bottom half of the main bearing. This here is the main bearing and this part here is actually the transverse girder. This transverse girder is part of the bed plate and it is fixed to this casing. In other words, it is not fitted only at this, it is fitted right from the center point up to the bottom pipe. So half a circle is the point of attachment for that, because the top part consists of the bearing keep, which can be taken out and fitted again, taken out and fitted again, but the bottom part is fixed on the transverse girder. So this force which is transmitted through the vibrating of the shaft is ultimately transferred to the transverse girder, which is part of the bed plate. Let's read what he says. When the crankshaft vibrates axially, this is the crankshaft, part of the crankshaft, and this is the flange, remember. And these are the seals. This is one side of the seal, this is one side of the seal, and on top there is the seal. One, two, and three. And you see there's a very narrow passage between the shaft and that seal. Shaft and that seal. So it's a thin layer of oil which is being compressed. It is not a massive volume of oil that is being compressed. It's a thin layer, even thinner than the thickness of the flange. So that thin layer of the oil which is compressed will have a tendency to go out through the orifice or come back through the orifice. If it moves in one direction, oil comes in. If it moves out, it is again compressed to be pushed out. So this is your axial vibration damper, and it is fitted, or rather welded, I think welded only. It is welded to the transverse girder at half the circle in the semicircle. So it gets maximum area for transmitting the energy. So when the crankshaft vibrates axially, the oil in the sides of the damping flange circulates inside the casing through a throttling valve. This here on top is the throttling valve. Actually, it is an orifice passage. If you close that valve, the orifice passage also reduces. And damping flange circulates through the casing through a throttling valve provided on one side of the flange and the other, which gives the damping effect. So we on board the ship never touch this. This has been set by the manufacturer. If it is to be touched, generally we will first observe that is excessive vibration. If this excessive vibration, then maybe we will require to reset this valve over here, which will regulate the quantity of oil flowing out and flowing in when the vibration is taking place. I suppose the vibration will increase if that orifice passage increases. If the orifice passage is reduced, then the vibration damping will be much more effective. In time, I don't have any experience on this particular area because we have never touched it. Right through the life of the engine, that axial vibration remains intact. Unless there is a survey and we need to dismantle it, then of course we'll need to do it. They will have a survey, they will check the orifice passage diameter and accordingly do the required setting. Okay. The casing is provided with high temperature alarm and pressure monitoring alarms located on both sides of the damping flanges. They give alarm if one side oil pressure drops more than the set value as a result of low lube oil supply, sealing rings failure, etc. Now, if the sealing rings fail again, then again the vibration will increase. That means there is no compression of the oil. That means whatever oil is being compressed is going out through the seal. So the vibration will increase. So these are factors which happen with the shaft if there is some damage. So one thing is the orifice can get damaged because of regular flow of oil can become bigger. Next is the seals, which which enable integrity of each chamber. That means the aft and the forward chambers have to have their integrity. That means oil must not readily escape from one chamber to another. Get it? So ultimately, when it compresses this side, the oil will go on through the orifice, or it will go to the next side of the flange. So that is how it is. Okay, let's move on. Balance weight. Now, apart from vibration dampers, we can have some amount of balance weights. These balance weights help in reducing the vibration to some extent. Where is the diagram? Yeah. Now you see, I had explained to you overlap of bearings. In the case of four-stroke medium engines, balance weight on the crank webs restricted to half the total reciprocating mass is fitted to the crank webs only for the odd number of cylinder inline engines. This reduces the resultant primary and secondary couple balance by about 50%. Now, never mind what he says about the proportions. These are all mathematical calculations which have come to these conclusions. But if you remember, we had a crankshaft where the crank pin was offset from the main axis of the crankshaft. Okay. Now, because it is offset, there is a mass which is offset from the main shaft. So when it rotates, this force, centrifugal force created by the crank pin offset, will be enormous force. So when you hold the shaft in one place, those bearings will be under a lot of load. To counterbalance this offset force, we need to attach weights on the crank web. And this is a diagram which shows how the weight has been attached. You see, this is the crankshaft, what you see, and at the lower part are weights which are bolted on the crank webs. So ultimately, what weight is offset by the crank pin is counteracted by the weight on the crank web at the opposite end. So if you have two weights on either side, then they are balanced of their forces. So what should be the mass of the weight? Well, theory says it should be equal to half the reciprocating mass. Half the reciprocating mass means half the weight of the piston assembly connecting rod. They are reciprocating. So whatever mass is there, half that mass is to be added on each crank web. All right. So that is how it is. In the case of a two-stroke slow-speed engine moment compensators are, you see, wheels, heavy wheels, which are fitted inside the engine to neutralize the primary and secondary couple imbalance. Here is your diagram to show you how the counterweights are fitted in four-stroke engine crankshafts. When you get the chance to go to workshop in college, the Yamaha engines that are there, those crankcase doors can be opened out. The nuts are kept loose. It is for you to open that crankcase door and have a look inside that crankshaft, inside that crankcase, and observe how the counterweights are fitted. Now, who has come? Rituraj. Okay, we have 66 boys. How many should be there? There should be a lot more. Pratham, I hope you keep the record of the attendance because I have to submit it. Otherwise, the office keeps poking us. Where have you given the attendance? Where have you given the attendance? So we are in trouble. And if they want to verify, they will go on to the lecture and they will find out who are being absent. So you better give the truth because those fellows who are absent and who are not being updated to the institute can find out, and then the consequences will be much more. So be a little truthful in whatever you do. It helps to avoid telling lies at a later date or trying to give excuses or getting out of form pressure. So this is one of the means of reducing vibration within the engine. In the case of four-stroke engines, you have counterweights on the crank webs, and in the case of two-stroke engines, you have moment compensators which are rotating or idling inside the engine. Okay, detuners. Now, we have spoken about axial vibration, we spoke about balance weights. Now, the third one, which is the most important one, is torsional vibration. Now, torsional vibration can also be reduced, and these are reduced by means of torsional vibration dampers. And torsional vibration dampers, the other name for torsional vibration damper is detuner. A detuner is essentially a torsional vibration damper. This detuner or torsional vibration damper is usually in the form of a floating mass. It is steel ring actually. This floating mass is also called an inertia ring. Okay, in the shaft system and are particularly useful in damping out torsional vibrations. This is achieved by changing the natural frequency of the shaft or shafting as the floating mass drives back into the shaft. A detuner is essentially a torsional vibration damper. Now, suppose you have a shaft which is prone to having torsional vibration. All right. On that shaft, you mount a casing through a flange. All right. And then inside that casing, you have a hollow space where a heavy ring can be fitted in. And before fitting in that heavy ring, you need to put in some fluid. That fluid must enable resistance of motion between the ring and the casing while it is inside. So you see, there is a heavy ring with a large moment of inertia inside here, and then a cover has been put on the top to enclose it. That ring is free to rotate inside on its own. To minimize metal to metal contact between the ring and the casing, we have a viscous fluid inside. That viscous fluid is usually silicone. Okay, and this silicone is sheared when there is relative movement between the ring and the casing. Okay, so when the shaft is moving, rotating, the casing will obviously rotate with the shaft. Suppose there is a vibration, that means the entire shaft is moving little, stopping, moving little, stopping, moving little, stopping. What happens? The casing will also be having the exact movement of the shaft. It will move, stop, move, stop, move, stop, move, stop. This is what is torsional vibration. But the ring which is inside the casing, when you move it, it will continue to move. And when you move it in opposite direction, first the ring has to stop and then follow up and start moving in the opposite direction. By that time, when it is started to move in this opposite direction, the casing is again moving in the ahead direction. So this counter forces cause some amount of dampening effect on the torsional vibration characteristic. Now, here is a diagram or a photograph of a torsional vibration damper. It becomes much easier to understand when you see a photograph rather than see a sketch. So you see the vibration damper, sorry, it is a circular equipment, and at the center you have an arrangement to fit the flange of the shaft. So the shaft is fitted right at the center of this damper, and it consists of a casing. This is the casing this is the casing that you see, and this casing is hollow space, and this hollow space allows for a ring, a very heavy steel solid ring to be fitted inside. Along with the ring, they inject or fill up with a viscous fluid. It may be silicone, it may be a synthetic material, it may be something which does not get damaged easily, does not leak out easily. Okay. So between the ring and the casing, you can see there is a shaded portion here and a shaded portion here. That is where the viscous liquid is. This viscous liquid is usually silicone, and it helps not to make a noise, not to have metal to metal contact, and give a smooth movement of the internal component relative to the external one. Okay. This movement is what causes damping out of the vibration, right? And because the fluid inside is being sheared, there is heat generation. This heat generation has to be dissipated. So how is it dissipated? Well, in this case, you have oil flowing all over the casing. So any heat from that liquid is transmitted to the casing, and the casing is continuously cooled with a shower. This shower is coming from the lubricating oil within the engine. Okay. This is one design of a torsional vibration damper. Here you see here another one, and possibly the ring over here is heavier, broader, and likely to cause more of heat generation. So to avoid the heat generation, you have a surface which has got a fin structure. Fin structure means thin plates on the casing. So this helps in dissipation of the heat energy that is generated on account of the relative movement and shear of the thick liquid that is inside the casing. I hope you are able to understand how torsional vibration dampers work. My earplug has come out. Just a moment. I accidentally pulled it out. So this is your torsional vibration damper. And in the exams, if you have to draw, this is an easier arrangement to draw. You need to draw an outside casing and then put a cover on top and show some bolts which are fixing the cover on top. Inside, you make a square section and put it down as inertia ring or heavy mass ring, and it gives enormous amount of moment of inertia. Enormous, because it is as far as possible from the circumference, from the central axis. It is far. This gives very good moment of inertia, which helps in reducing the torsional vibration. Definitely, this diagram is a lot easier to draw as compared to this. So similarly, for your axial vibration, if you are required to draw a diagram, I think this diagram is inevitable. But do not draw this right-hand side part of it, because the right-hand side part of it is the torsional vibration damper. You see, the torsional vibration damper and the axial vibration damper both are fitted to the free end of the engine. On the free end of the engine, you have a flange, and on that flange is bolted the torsional vibration damper. And before the flange, there is another small flange on the shaft itself, which is part of the axial vibration damper. So this is what constitutes the axial vibration damper, and this is what constitutes the torsional vibration damper. Okay, okay. That is all for right now. And let us go. We will take a 10-minute or 5-minute break, and we will start again with the new PowerPoint program. So let me also have a little bit of hot water, and I will come back again with a new PowerPoint, and that is this one, PPT2. Yeah, yeah. This is your next PowerPoint program, and we will have this one. Sorry. Okay. Oops. Let's take a break for a moment. I want to go and drink some hot water. My throat is feeling sore. So just be there. Do not go away. He's not wearing anything.
Hey now, she's already sneezed.
Huh?
She's already sneezed 5 times. Now she's worn a jacket. Pinky. Weather is weird now. You don't understand. Suddenly thanda, suddenly garam.
Okay, folks, I'm back and I've got my hot water here with me. And let me put on the camera once again. Yeah. Hope you can see me. I can't see myself. I don't know if I'm visible to you at all. All right. Now that we have finished the forces and stresses in the engine component, we are going into the next part of our syllabus. And that part of the syllabus is much more interesting than what we've done earlier. So that part of the syllabus is fuel systems and metering devices. In other words, now you're coming into the thick of becoming a marine engineer on board, where you'll be dealing with fuel pumps and the engines directly. You will not be dealing with so much of torsional vibrations and axial vibrations. Those are predetermined by the manufacturers and arrangements have been made. At the most, you will be finding out pipes which are vibrating or machines which are vibrating, and you will need to identify the cause of the problem before you actually solve the problem. For any issue, any problem inside the engine room, we have something called root cause analysis. This root cause analysis means that you have to identify the cause of the mishap or cause of the failure. You cannot simply repair a pump because it was broken. You need to find out why it has broken and thereafter eliminate the cause for why it is breaking. Otherwise, if you simply go and repair a pump or a machine because it was broken, it will break again because you have not removed the cause for the breakage. So that is why, as engineers, you need to identify the cause of a failure before you actually go forward with the repair. Remember this, this is part of being an engineer. When there is a mishap, identify the cause, eliminate that cause, and then do the repair. That is the key to being a successful engineer. Okay, let's move on and we go on to our subject. It is fuel pumps and metering devices. Metering devices means devices which are giving in regulated quantities, delivering in regulated quantities. The fuel injection system is one of those metering devices. Okay. The fuel injection system is very important to the efficient operation of the engine. Four functions are to be satisfied. We are starting out with the most important part of the engine, the fuel delivery injection arrangement. You already have some idea of what a fuel injector is like. Now we will go into what the fuel pumps are like. They are a little more in detail, and nevertheless, once you get the understanding, everything becomes very comfortable. So the fuel injection system being a very important part of the engine, four functions are to be satisfied. These four functions should be well known to you before any examination. Number one, deliver an accurately measured quantity of fuel to each cylinder regardless of load. That means it doesn't matter what the load is, but the quantity delivered to each unit must be the same. Okay. Next, deliver the fuel at the correct time at all loads with rapid opening and closing of the fuel injection valve. That means the fuel has to be injected at a particular time for all the units. And when it delivers, it should quickly open and close. As quickly it should deliver and stop. That is what is required of the fuel injection valve. Number three, inject the fuel at a controlled rate. Now, controlled rate here would be considered in terms of microseconds. Now start thinking in terms of microseconds. See, once the fuel valve opens, the fuel is discharged, and it keeps discharging till it stops. All right. The rate at which it discharges must be uniform. So that is very essential. Now, I had explained to you what is diesel knock, ignition delay, ignition lag, that is. Now, you see, why he has said the controlled rate has to come. Inject the fuel at a controlled rate. When the fuel comes into the combustion chamber, it does not ignite instantaneously. There is a delay. During this delay period, some more oil keeps coming in. And when the combustion actually starts, the entire mass of fuel that has come in combusts. Okay? But the fuel coming in is still in process. So when the combustion takes place of the oncoming fuel. The oncoming fuel does not have any more ignition delay. So the rate at which the fuel is coming in must be a controlled rate. It must not be an complete full mass coming into the system. Then there will be a detonation. So the rate at which the fuel comes in after the combustion started has to be a controlled rate. And this is achieved by having the diameter of that nozzle to a particular value relative to the length of that passage. So the length to the diameter is to be 4:1, if you remember correctly. I hope you are able to understand. I don't know. I'm putting in my effort. It is up to you to take an effort to understand. If you don't have, if you have difficulty in understanding, do not hesitate to ask a question on the chapter, on the chat column. Okay. The next point, what we have is the atomization and distribution of the fuel in the cylinder without impingement. So this is another demand made of the fuel injection system. You need to atomize and penetrate the fuel into the combustion chamber correctly without causing impingement. That means the fuel must not strike any of the combustion chamber walls, which is a big demand. It is not a small demand. So the requirement for this is significant. So your fuel injection system has to be in top-notch quality and order to ensure that the engine is able to run satisfactorily. It is very, very essential. So your injection system is considered as the heart of the engine. If the injection system is not good enough, the whole engine is not good enough. You can have a very good engine, but if your injection system is not following out what these 4 points are stipulating, then engine is not going to run satisfactorily. This is understood. Okay. All right. Let's go to the next bit. Any questions? Do you have any questions? If anybody has any questions, do not hesitate to ask.
Sir,
Okay. Please
sir,
explain the
sir,
okay, please explain the first point. Deliver an accurately measured quantity of fuel to each cylinder regardless of load. Okay. Suppose the engine is running at half a slow ahead. Let us say slow ahead. It is running at slow ahead. Okay. Now the injection system, it has to deliver a certain amount of fuel because the RPM has to be much less than the full speed. It has to be, let us say 110 is the full speed. We want to run it at say 40 RPM. That is slow ahead. So at 40 RPM, you cannot give too much of fuel to the unit. You have to give a little amount of fuel. But that little amount of fuel has to be exactly that amount for each unit. All right. Suppose you are giving in 20 grams of fuel for each injection. So 20 gram, 20 gram, 20 gram, 20. All of them must have 20 grams. You cannot give 25 grams here, 21 grams there, 23 grams there, and 20 grams there. Then all the units will be differently loaded. So then you will have a very unbalanced engine. Balancing of engine is not only physical balancing. That means with balancing weights, dampers, and these things. There is also something called power balancing. Power balancing and mass balancing are two different chapters. Power balancing is ensuring that each unit is giving equal power or contributing to equal power. Okay. So deliver an accurately measured quantity of fuel to each cylinder regardless of load. That means when the load is low, small quantity, 20 gram, 20 gram, 20 gram, 20 grams correctly measured and delivered. Now when you increase the load, say half ahead, you come to 60 RPM. Then this one will give 40 grams, this one also has to give 40 grams, this one also has to give 40 grams. All of them, all the units will give exactly 40 grams of oil when it is on half load. Now when the engine is on full load, you have to give 100 grams each time the fuel injects. So each of them must give 100 grams, not 90 grams, 95 grams, 110 grams, 105 grams, not like that. So your injection system should be such that it is capable of giving equal quantity of fuel from each of the units at any load, half load, full load, quarter load, whatever load is there. All right. We also have to control the air intake. Air intake is not really controlled in the sense it is given depending on what is the scavenge pressure. If the turbocharger can give more pressure, good enough. You don't need to control the air much. It is always the amount that can come in at the requisite pressure because the timing at which the air is allowed to come in is fixed. Okay. And if the pressure is also fixed, then will be a certain quantity. You have to maintain, you have to control the air pressure. All right. The air pressure is determined by number one, the electric blowers. These electric blowers are used when the engine is running at part load condition. That means the turbocharger is not capable of delivering air to the engine. So that is the time you put the automatic switch on for the electric blower. And the air quantity coming in will be regulated. Now when the engine RPM keeps increasing, of course, it has to increase slowly up to the full speed. As it keeps increasing, the discharge from the exhaust will also be increasing. So the power supply to the turbocharger will also be increasing. So if the supply to the turbocharger is increasing, then the scavenge air supply will also be increasing. So it is self-controlled. The whole process is self-controlled. And our air is being drawn by the turbocharger is not being restricted by a contaminated or an obstructive filter. Okay, Mrityunjay Kumar Rana has, what will happen if we supply unequal fuel to each unit? Good question. And it sometimes happens. It sometimes happens when one fuel rack of a pump is stuck and it is not able to give more fuel. So what happens? Then if one is giving more fuel, it is going to develop more power. The other one will develop less power. And how is it observed? Because you can't see power. It is an abstract quantity. How will you see power? So what they do is they have exhaust gas temperature dial gauges. Exhaust gas temperature dial gauges. They are not like thermometers. So the dial gauges will indicate what is the exhaust gas temperature. And as a thumb rule, the best means to know how much power a unit is developing is determined by the amount of combustion that is taking place. And the amount of combustion that is taking place in the engine will determine that exhaust gas temperature which is leaving the unit. And if you burn less fuel, then the heat generation will be less, the temperature will be also less. So one look at the dial gauge, which will show low temperature, will be directly indicative that this unit is not developing enough power. What could be the reason? The reasons could be so many, so many. But now that you have said that we are giving unequal fuel, so all the units will show all different temperatures. The exhaust gas temperatures of all will be haywire. Your objective is to get them as close as possible to the same value for all the units. With a little consideration, some pressure gauge may not have an efficiency of 100%, others will have 95%. Maybe the needle inside is not able to move at the same rate as another pressure gauge. So plus or minus 3 to 5% error in the gauges is permissible. Okay. Plus, it is not possible that all of them will be exactly the same. It never happens. I will say up to 5 degrees plus or minus is variable in show. And in spite of giving as close as possible equal amounts of fuel, the peak pressure will not be the same. Why? Because some of the piston rings may not be as good sealing as the others. All right. In some case, maybe some scavenge ports may be choked. So the quantity of air going in will be also little less. So the consequence is how much power it develops. So all the units, though we are trying our best to get equal power from all the units, none of them gave the absolutely equal unit. There will be little error from each of them, but this is permissible within a certain margin. A certain margin is permissible. Okay, Mrityunjay, Rana, so that is what will happen. There will be an unbalance of power, and that will show up in the exhaust gas temperatures. And then you are required to find out what is the problem. So, do the vibration will increase if the fuel supply is unequal? Marginally, there will be a difference in the vibration in one unit, but nothing of consequence. And one of the best ways to find out if the injection is good or not good is to feel by hand the pulse which is coming in that pipe from the fuel pump to the injector. You will find a pulse, and that pulse has a certain intensity. That intensity actually, our human bodies are the best sensors. That pulse that you feel, and you feel the next one, the pulse, and you know if there is any difference. Similarly, you feel all the pipes for their pulses. You find suddenly one of them pulse is very low. Then you look at the exhaust gas temperature, you will find the exhaust gas temperature is low immediately. Or if you look at the exhaust gas temperature and see it is very low, and you feel the pipe, the pulse is also very low, then you immediately know that the quantity of fuel is not going in correctly, because that pulse is indicative of how much fuel is going in and the valve reseating after the fuel goes into the injector. Once the fuel is cut off, for every combustion process, there is a delivery valve in the pump, and that reseats. That impact of the seat is what sends the pulse right through the piping, part of it. Okay. Okay, sir, flow meter before and after each unit will show. You don't have flow meter before and after unit. You have only one flow meter for the entire pipeline, which is going to the engine, and another flow meter which is returning from the engine in totality. No individual flow meter. Otherwise, Kartavya Singh, you'll be spending your entire 15 linear duty writing flow meter reading. If every unit has a flow meter, you will be spending your entire time in the engine room reading flow meter readings. But anyway, good that you are getting yourself clarified on these small issues. Okay, you cannot have so many flow meters for every unit. No way. But the fuel pump itself, which controls the fuel quantity to the engine, is worked with the help of a fuel rack. This fuel rack has a scale on it. Okay, this scale has got readings from 0 to 90. So your duty is to check whether that scale and the pointer are showing same for all the fuel pumps. It so happens at some time the fuel rack gets stuck. It gets stuck at 40 when it is supposed to be at 60. So then immediately you have to put a little lube oil, free up the rack and ensure that the fuel rack has come up to 60 to give the correct quantity of fuel. For that, we need to study the constructional detail of the fuel pump, which we will do today. Divakar has another question. Sir, then how do we know the amount of fuel in each unit at a time? That's what I said. You don't really know how much fuel. Only indicator is the fuel rack on the fuel pump, which is moved in totality. That means all the fuel racks are connected by one lever, and that lever is connected to the governor. So the governor moves that lever, which will move all the fuel racks together. But these fuel racks are moved with a spring lock. In other words, if one fuel rack gets stuck, it does not mean that the governor fuel rack will get stuck. You get it? It will remain stuck. But the other units will all move to 60, value 60 on the scale, which is marked on the fuel rack. So that reading that scale is the only way to know how much fuel is going into the engine. Okay, Divakar, we will come to this reading the fuel rack. I think I have missed out something of marking the scale on the diagram. Okay, I will improve on that. Okay. Okay. So I hope you have understood these four. Any more questions? Definitely you must ask and get these points cleared before we go on to fuel pumps. What will happen if you supply unequal fuel to each unit? Then unequal power will be developed and the engine will be unbalanced in the power domain. The balancing is physical balancing and power balancing. So in the power balancing, the engine will be unbalanced. Okay, that is Mrityunjay's question. Next question is Rahul Kumar. Sir, do the vibration will increase if the fuel supply is unequal? Yes, to some extent it will be increased, but it will not be so visible if the differences are small. The one way to identify the decrease or increase is to feel the pipes of the injection pipes. That means the pipe from the fuel pump to the injector. There will be a definite intensity of the pulse. In fact, these pipes are tested to a hydraulic pressure of 1000 bar. It is as tested like your common rail. These pipes are very strong. And if you see the pipe, it is about let us say 1 inch diameter for a big engine, 1 inch diameter. So 1 inch diameter is quite a big pipe, but the hole inside the pipe is the diameter of a pencil. So you can imagine how thick the wall of the pipe is, because it has to take that pressure of 380 bar and it is tested to a pressure of 1000 bar. before it is utilized. So that is why this pulse from 0 to 380 bar and suddenly to 0 creates an enormous pulse. And this pulse can be felt on the pipe of the injector. Okay, so that is how you know that the vibration increases or decreases. Flow meter before and after each unit will give us the amount of fuel consumed. No, Kartavya. We cannot afford to have so many flow meters. There is only one flow meter which sets the oil. I think fuel pipeline I've given you. And there is a flow meter which allows the oil to go to the engine. And what is not consumed by the engine, the oil comes out and it comes out through another flow meter and it goes to the buffer tank, which is also called the banana tank or mixing tank. So these two flow meters will indicate the actual consumption of the fuel. Okay, so amount of fuel in each unit at a time. So then how do we know amount of fuel in each unit? We don't know except that reading on the scale of the fuel rack, which is on the fuel pump. Okay, let's go. Good. I like everybody asking questions to get it cleared. And I'm sure this PowerPoint program, there will be hundreds of questions coming from you. See, teaching fuel pumps online is not easy. I would rather have you fellows in front of me and the pump also in front of me. Then I can explain to you, and what you see, your interest gets generated much more. But if what you hear, the interest is not so generated. But I will try my best to explain it as clear as possible. And when we do get a chance, we will actually have the pump between in front of you and me. And there I will be able to explain to you all the parts and how it works. Because this pump is not at all like any other pump that you have seen. Okay, let's start. The opening and closing of the fuel injection valve is controlled by the fuel pressure delivered by the pump. That everybody knows. Okay, so it is like hydraulic pressure which opens the fuel injector. Broadly, there are three types of fuel injection modes. Okay, one is called the jerk injection. It is called jerk. Why it is called, don't ask me. I don't know why it is called. It is called jerk injection. And it is, sometimes termed as solid injection pumps. Now, this term solid injection is to be well understood. Why is it sometimes called solid injectors, solid injection system? It is called solid injection system because the fuel, and for that matter any liquid, is incompressible. You cannot compress a liquid like you can compress air. So that is why the pump which delivers oil to the injector, the pipeline which is got full of fuel, when it compresses here, there is instantaneous result at the other end. Why? Because the fuel cannot be compressed. You put the pressure here, you will feel the pressure at the other end. It is called hydraulic system, but sometimes it is called a solid injection system. The term solid over here is a misnomer. It is used because liquid is incompressible. So a solid injection means when the liquid is compressed, that liquid instantaneously delivers. There is no scope of compression. If the pipe had air in it, you can compress and nothing will be delivered from the other end. So that is why we need to prime the lines. Priming the line from the pump to the injector means purging of the air inside that pipe. If there is oil and if there is air, when the pump pumps, the oil is not going to go into the injector. That air is going to compress and decompress, compress and decompress. Each time the pump works, there will be no fuel injection. So it is imperative to ensure that the highest part of the fuel injector and pipe, the nut is little loosened out and the air is allowed to come out. And the moment the oil starts coming out from there, you close the nut. So there is no more air in the system. Now it will have solid injection process, which means when there is pumping action at the pump, there will be delivery at the fuel injector without any compression or change in the volume of the entire fuel enclosed in the system. I hope you are able to understand. Divakar, have you understood what I've said about solid injection?
Yes, sir.
Okay. Okay, Divakar, let's move on. So this jerk injection can also be termed solid injection, and it is termed solid injection because liquid is incompressible. For that matter, fuel is incompressible. Now, this jerk injection pump, there are two types which we are going to study thoroughly. One is the Bosch type, and it is the most common type of fuel pump. Everywhere you go, you'll find Bosch type of fuel pump. The second one is the valve control type. This is also a very important one, and Sulzer and its licensee manufacturers, they are the ones which use the valve control type. Both are very important, both are brilliant designs, and if you have any other design, possibly there are other designs, but most of them are, makeshift. The second system that we have where fuel injection is made is the common rail system. I will not elaborate on this at the moment because I want to focus on jerk injection. Okay. And common rail system, I gave you a brief description about one pump which is driven by the engine develops pressure to fill up one pipe, big pipe, strong pipe, and this pipe is capable of taking 3000 bar pressure. And this works also like a tank, and this tank is under very heavy pressure, and from this pipe or manifold you have individual pipes going to the individual injectors, and these injectors, the fuel is received right at the nozzle at 2000 3000 bar. Okay, so all it needs is momentary opening of that injector to allow the oil to come in. So this injector is operated by means of a computerized signal, and that signal will come to the injector, which may be of a variety of designs. It may be piezoelectric, it may be solenoid, or it may be hydraulic, all three. Okay, so this common rail system is entirely different from our present system of jerk injection. We will focus on jerk injection as of now, and after that, at some stage, we will go in depth with common rail system also. Next is timed injection. Timed injection is not a very common process, and I have seen it only on one ship, and that was our Kirloskar engines with Cummins collaboration, and they had the small engines where they had this form of injection. Here you have pressure and time. Oh my God, it's already 11 o'clock. Pressure and time. Let's do this plate and one more plate, then we'll go into the other. Pressure and time are the two factors which determine the fuel injection process here. Now, going back to the jerk injection, this is the most common process employed on marine engines. The pump consists of a cam operated plunger in a barrel with very fine tolerances. It is same as piston and liner, but here there are no piston rings. The piston itself seals the chamber above the piston. So you can imagine how fine the clearance is between the piston liner and the piston, because that has to compress oil, and oil can be very thin, and if the oil leaks past the piston, then there will be no compression. So that is why the barrel and the plunger, they come as one unit. They are matched with each other. There is only working clearance. Even liquid cannot pass through the passage between the piston and the liner. That piston and the liner. In the pump, they are called plunger and barrel. You have piston and liner for the engine, and for the fuel pump, you have plunger and barrel. And these two are matched with each other. You cannot use one plunger for another barrel or another barrel for another piston. The pump and the barrel, the plunger and the barrel, they come as one unit, and they are matched to maybe 1 micron clearance between, or other just working clearance. Okay. So this is the most common. The pump consists of a cam, plunger, and barrel. Next, the hydraulic electrically compressed fuel pressurize the needle valve in the injector to lift and allow the fuel into the cylinder. This everybody knows. Okay, that is how the Bosch pump works, plunger and barrel. The second type of jerk pump is the valve control type, and this valve control pump is largely used in Sulzer engines. Okay, so these are the two different types. One is the plunger and barrel, one is consisting of suction and delivery valves, or two different valves. They open at their sequences to control the quantity of oil going into the pump. Controlling the quantity of fuel delivered is the responsibility of the pump. Okay. And that quantity is finally controlled by the governor signal to the pump. The valve control pump is largely used in Sulzer engines. Here the common rail system. A little word about the common rail system also. Here a single engine operated pump delivers fuel to a common pipe or manifold, which is called common rail, because it is connected to so many units. So that is why it is called common rail. Separate high pressure pipes are led, is this correct? Led to individually controlled fuel injectors on the cylinder heads. That I told you just now. Okay. Next is, this is the last because it's already 11:06. Control of these injectors is computerized, and operation of the injectors may be electronic meaning piezoelectric, hydraulic, or electrical by itself. That is solenoid. The solenoid will operate the fuel injector. Modern common rail engines do not have camshafts. See, the common rail engine of modern times does not have any camshaft. Very few engines you will be facing on board. Most of them you will be facing are still with camshaft. It is going to continue for a long time. But the very modern engines which you need to be aware of do not have any camshaft. Even the exhaust valve operation is computerized. Even the air starting system, which earlier required a distributor to operate, do not have the same distributor. They are electronically or electrically operated solenoid valves, which operate in sequence depending on the firing order. So a lot of electronics has come into marine engine, and you, as a marine engineer, you now need to be an electronics engineer also. I cannot tell you anything any less relevant. Okay, so be a little focused on electrical and electronics subjects that you study in your syllabus. Okay, we'll call it a day today, and this will be all as of now. So next class we will continue from, what is this page number? Number 5. Okay. Farhan, remind me, next class we have up to class 5. If you have any questions, you can ask now, because I am stopping the presentation. Any questions you need to ask, you have about 5 minutes more before your next class starts. Any questions? No questions. Wow, everybody has understood. Okay, that will be all for today, and we will discuss this more. And I am expecting a lot of questions regarding this fuel pump, because this is part you have to be very, very clear about. No questions at all. How does the Bosch pump work? How does the valve control pipe? What is effective stroke? What is idle stroke? What is total stroke? Everything will be coming in the forthcoming class. I'm still in the preparation of continuing making out these PowerPoint diagrams and literature. So I'll try my best to have you understand this part of the subject very, very thoroughly. If you have any questions, never mind how ridiculous it is, you ask. Okay, bye-bye and take care.
Thank you, sir.
Okay.